Let's look at history a little bit about the key players that are responsible for the advances we have made in climate modeling and weather modeling. You can go back all the way to Haley and Hadley, who had proposed Hadley cell circulations before understanding Coriolis, and then Coriolis himself quantified the Coriolis effect. There are a lot of key discoveries along the way, but Wilhelm Birknes, 1860 to 1951, who is now considered founder of dynamical meteorology. He established the Bergen School in Norway, and his son Jakob Birknes is the one who has big name in the ENSO processes, where he showed that the ocean-atmosphere coupling and the feedback between sea surface temperature gradient and wind anomalies in the deep tropical Pacific are key part of the El Nino. So Wilhelm Birknes was the first one to propose that governing equations to be integrated forward with initial conditions were key for weather prediction. Of course, that time there were no computers yet when he started this, and he didn't have all the details of the simplifications that could be made, or things like data simulation for initializing the forecasts, which are critical now and have improved the forecast skill and extended the lead times of the forecasts from let's say 1 day to 3 days to 5 days, and now even 7 days, especially in the southern hemisphere where there is not much land, a lot of ocean. So when you have a lot of ocean, observations are difficult. So initializing the model means prescribing the conditions now at every grid point on our model, in terms of temperature, humidity, winds, and other critical variables, and then you integrate forward. We'll see that small errors in this initialization can make big problems. So the first actual experiment in forecasting was made by Lewis Fry Richardson in the UK, and he just took some profiles from observational network that was in fact established by Wilhelm Birknes and tried to make forecast for 24 hours over Europe. He made a model with a certain resolution of 3 degrees by 1.98 degrees, so approximately 300 kilometers by 200 kilometers. We will see what that means later on, but you can imagine that if your box over which you're computing weather and climate is that large, then you know that clouds are much smaller, land characteristic changes on a much smaller scale, and so on and so forth. So those can be issues, but he had to make a compromise, because at that time he imagined people sitting with slide rules and getting fed information. So this is the schematic representation of how Richardson's experiment was construed. So he was getting observations in a central system, and you can see the steps down here from the observational towers with people sitting in rows here, and each one would compute something and pass it to the next person and then the next person. So that was a numerical integration like a computer at the time. And it was a remarkably bold experiment which took, I think, 3 months to integrate for 24 hours, and there were problems, of course. But Richardson did live long enough to see the computer survive, and the early efforts in forecasting led by people like Charney succeed in demonstrating that numerical forecasts are possible when used for certain regions with certain simplifying assumptions that did not solve the global high-resolution models like we do now. So Richardson did publish, I think in 1923, his vision of how numerical forecasting can be done with thousands and thousands, tens of thousands of people sitting with slide rules and making the computations. So The other key player in this was Rossby, Carl Gustav Rossby, who was the first one to recognize that vorticity is a key player in generating especially mid-latitude weather. In the tropics it's much more of convection, so rapid heating, rapid rise, vertical motion, and rainfall, which can happen very fast. So even now there are difficulties in forecasting weather in the tropics compared to mid-latitudes, as I said before, where systems lumber around for 10 days and make it easier to predict. So the vorticity idea was that when you displace air mass, it is constrained by changes in vorticity and vorticity conservation. So waves always require a perturbation force and a restoration force. So in a rotating tank, you can see from University of Washington, I think this must be Peter Ryan's setup, who was another amazing guy who is another amazing guy who has done a lot of fundamental work. So you can see the waves being generated. If you are a weather buff, you might have already seen that this kind of can be imagined as the North Pole here and the jet stream going in its wavy pattern around. Those waves where the restoring force is the planetary vorticity got named as Rossby waves after Rossby, who was the first one to propose this. So you can see here Rossby wave patterns over the North Pole. So you can see cold Arctic air is being separated from the warm tropical subtropical air by this referee, the jet stream, which is westerly, so goes from west to east. And you can see that this is uninterrupted upper airflow pattern, waves forming in the polar vortex. We haven't defined the polar vortex here, but it's actually different than the jet stream. It is the stratospheric feature that matters, puts down weather down to the surface. And you can see once there is a displacement, you have low pressure, high pressure, low pressure, high pressure kind of wavy pattern. And in the third phase, you have high pressure center. So cold air obviously has high pressure. We saw that. Did we see this? Maybe not, but you can look up my other courses and podcasts about how to first order surface pressure relates to temperature. So warm air will have high pressure, cold air will have warm air will have low pressure, cold air will have high pressure. But here you are talking about perturbations which associated with the waves. So upper air waves becoming more pronounced, so you begin to pinch off a little piece of the cold air, cold polar air, and then take it off from the main jet stream. So initial pattern restored with the detachment of a cold air mass. So you can see here why people get puzzling temperature changes. Sometimes you will get much colder temperature, let's say in the east coast here of US and Canada, whereas you may get much warmer air intruding from the lower latitudes into the higher latitudes and creating heat waves on the west while creating colder than Mars temperatures on the east. And there can be times when Alaska has much warmer temperatures around Christmas than Washington DC. So this is created basically by these wavy patterns, and Carl Gustav Rossby was the first one to say these can be used for not exactly these features, but waves like these create patterns that are persistent. So when things persist, then they are easier to predict, because if you observed this and then you could see some other pressure patterns, then you could probably predict this, for example, cold air mass over Central Eurasia over here, and warm air over here in parts of Europe and Middle East, and so on and so forth. Okay, so that's how the mid-latitude wave weather pattern were made possible in terms of predictions based on Rossby's ideas. In the 1950s, even as computers became available, mainframe computers became available, like the ENIAC at IBM and UPenn, Ed Lorenz at MIT wrote some really simple looking equations and integrated them. He represented the weather with three equations which had critical nonlinearities in them, and showed that small perturbations to the initial conditions, let's say you are initializing a weather forecast over the US, and you are prescribing temperature, vertical profile of humidity and winds, and then you made a small error in one of the profiles or temperatures, then he showed that within few days this small error can grow into a large error and make the forecast basically useless. Errors grow rapidly in nonlinear systems, and he introduced the idea of chaos theory, and became a massive field of interest for a while. Has kind of subsided because of lots of other things happening along the way. But this is how his equations looked. I took it from this website here. So you have x, y, and z representing, let's say, three variables, and how they are related to each other. So x, time rate of change of x depends on y and x with some parameter, y depends on z and y, and z depends on x, y, and z, and integrate and plot x, y, and z, and you can see how it evolves into this strange butterfly pattern, which became well known as the flapping of a butterfly wing in US, then generating a hurricane in Europe, and so on and so forth. There are lots of details here about self-similarities, strange attractors, dimensionality of the systems, and so on and so forth. But an easier example to understand is here, the double pendulum, where you have one pendulum attached to another pendulum which swings around kind of easily. Some parameters like how much perturbation is given initially and so on can be changed by a little bit. So you can see theta 1 is 0 and 0, theta 2 is 0 and 0.1, and you can see how differently they evolve over time and how the system goes completely chaotic as we integrate along. So we mentioned the Clausius-Cleperon equation and the warming of the air, more humidity, humidity condensing, forming clouds, rain, and so on. So thermodynamics of the water vapor tends to be one of the biggest nonlinearities in the system, and obviously in the tropics it's a key player as well, where warm air rising with evaporation, condensation can begin to drive waves and winds and convection and so on. So they can evolve very rapidly in time, which makes it harder to predict as well. Okay. Suki Manabe, one of the guys who won the Nobel Prize for Physics in 2021 for his climate work, was one of the first ones who pioneered the idea that atmosphere cannot be integrated alone if you want to do climate. So he developed the first ocean atmosphere coupled model with Kirk Bryan, and then he made incredible number of experiments by increasing carbon dioxide. And there are what are called biases in the models, as we said before. So if you just give it top of the atmosphere radiation from the sun and give it representation of the atmosphere, ocean, and land, for various reasons of process representation, parameterization of processes, small scale processes like convection, mixing, and so on, models tend to drift away from reality because they begin to not do the energy balance properly, including because of these multi-scale processes in space and time. So he invented a method called flux correction, where he would just pull the model back towards reality by adding or subtracting fresh water and energy, which is not done anymore because it's considered not a good idea, especially when you make future projections. But nonetheless, He's still very active, and he still insists that flux correction is a good idea because the models continue to have biases and so on. So this is how the models evolved in the net. By the mid-1970s, we had atmospheric models running routinely. Mid-1980s, we had atmosphere, land surface, ocean, and sea ice models. And then they were developed independently, but then they got coupled. There were coupled models being run by Manabe already around here, because Cleperon had developed the first ocean model at Princeton GFDL also in the 1960s. The coupling happened here more routinely now, early 1990s, when the first assessment of the IPCC came out. Atmosphere, land, and land surface and ocean and ice were coupled. Then models were independently developed as sulfur cycle model, and carbon cycle model, ocean carbon cycle model, atmospheric chemistry model, and you can see that atmospheric chemistry remained that way till the 2000s. Only in the late 2000s now we are having active atmospheric chemistry being coupled as well. So you can see sulfate aerosol models got coupled here, non-sulfate aerosols and carbon cycle got coupled here. Now we have dynamic vegetation coming in, atmospheric chemistry, dynamic ice sheet models are now coupled as well. So many of the new CMIP 6 projections being released now as AR6 assessment report 6 under IPCC. Many are running these kind of dynamic ice sheet models. The questions remain about whether increasing complexity and sophistication of the models actually increases their realism and so on. Those are issues one has to deal with, in the sense that when you add dynamic vegetation and carbon cycle, you can do carbon cycle here without vegetation, but when you add them together, you have to also worry about what happens if they feed back with each other and if they don't feed back with each other. So the trajectory of the climate and the warming, etc., will be very different depending on whether they will interact with each other and feed back to each other or not. Similarly, whether sulfate aerosols and non-sulfate aerosols will only affect radiation, or will they also affect the cloud microphysics and so on. Those things also begin to influence the solutions. So one has to be very careful when you add new components as to what assumptions you have made and what is not being specifically included in terms of feedbacks, etc. Okay, so we'll come and look at some examples of climate modeling that goes on now and their applications before we move on to the next chapter. Okay.